Temperature dependence of the rate of a reaction. Rate of all reaction increases with increase of temperature. For 10-degree rise of temperature, the rate constant of a reaction gets doubled. The effective temperature on rate of chemical reaction can be calculated by the temperature coefficient. For example, the rate constant at 298 Kelvin and the rate constant at 308 Kelvin. The temperature coefficient, the effect can be calculated by calculating the rate constant at two different temperature. The effective temperature on rate of chemical reaction by showing different examples. For the first one is a decomposition of nitrogen pentoxide. At 25-degree rise of temperature, the rate constant increases by 43 times in decomposition of nitrogen pentoxide. And also the another example, the reaction between KMnO4 potassium permanganate and oxalic acid during the titration or reaction. Here the faster decoloration takes place at the increase of temperature or at high temperature. Arrheniusequation. Temperature dependence of rate of chemical reaction. The temperature dependence of rate of chemical reaction proposed by J.H. Van 't Hoff. Physical justification and interpretation made by Arrhenius. The effective temperature on rate of chemical reaction given by the equation K is equal to AE power EA by RT. Here the term A is Arrhenius factor, frequency factor or pre-exponential factor, and it is constant and it is specific to a particular reaction, that is collision frequency, and EA is energy of activation, R is gas constant, T is at a particular temperature. According to Arrhenius, a reactant A reacts to form the product C. Before forming the product C and B is the intermediate activated complex formed, the intermediate or activated complex breaks or decomposes to form the product C. Now consider a reactant A to form the product C, or otherwise, for example, hydrogen and iodine reacts to form the product hydrogen iodide. Here, during the formation of hydrogen iodide from hydrogen and iodine, the bond between two hydrogen atom breaks, the bond between two iodine atom breaks and starts forming the bond between hydrogen and iodine. Here this state is called the intermediate state, a transition state or activated complex. The hydrogen and iodine molecule collide to form an intermediate. Hydrogen and iodine molecule collide to form an intermediate that breaks up to form the product hydrogen iodide. The next one is the term called activation energy. What is activation energy? When a reactant forms the product, the intermediate formed at the transition state is called activated complex. The energy needed to form this intermediate activated complex is called activation energy. All reactant molecules are not converting into product. Only the reactant molecule which possesses the extra energy called activation energy are converting into product. So thereby we can define the activation energy as the extra energy required by the reactant molecule to form the product. The extra energy possessed by the by the reactant molecule to form the product is called activation energy. That extra energy results in effective collision. How the extra energy came is results in effective collision between the atoms and molecule. That extra energy is helpful for the formation of product. That extra energy is called activation energy. So again I am repeating, what is activation energy? The reactant molecule not directly converting into product, it forms an intermediate or activated complex or transition state that breaks up to form the product. The energy needed for the formation of intermediate activated complex is called activation energy. It is the fact that all reactant molecules are not converting into product. Only the reactant which possesses the minimum energy to cross the energy barrier to form the activated complex or converting into product. So, the extra energy needed by the reactant molecule, the extra energy needed for the reactant molecule for the activated complex, that energy is called activation energy. How the activation energy comes? The activation energy comes for the reactant molecule from effective collision between the atoms and molecule. That is helpful for the formation of the product. If the molecules possess more activation energy, the more will be the product. So, the activation energy comes from the effective collision. More will be the activation energy, more will be the rate of reaction. Now, consider this graph or see this graph. Here the y-axis, the energy is plotted, in the x-axis the progress of reaction. Here the reactant molecule, the state, and here it is the product. The reactant molecule, here the energy of the reactant molecule increases and it crosses the energy barrier and converting into product. Here the energy change during the conversion of reactant into product. Here the extra energy possessed by the reactant molecule to cross the energy barrier and converting into product, this extra energy is called energy of activation or activation energy. Next one is enthalpy of a reaction. When the reactant forming the product through activated complex, energy released during the process. The hydrogen and iodine react to form hydrogen iodide. Here the hydrogen and iodine is the reactant in one energy state and hydrogen iodide is in another energy state. The difference in the energy state of product from the reactant, that is called enthalpy of a reaction. Difference in the enthalpy of reactant hydrogen and iodine, and to form hydrogen iodide, the energy difference, the enthalpy difference will give you the enthalpy of a reaction. And what is the transition state is, or activation energy is, the energy difference between the reactant and the transition state, that is called activation energy. That is the energy of transition minus energy of the reactant. Here the energy of transition and the energy of reactant, the difference will give you the activation energy. The energy of the reactant and the energy of the product will give you the enthalpy of a reaction. The next explanation of effective temperature is the effective temperature on number of collisions. The temperature increases, automatically the kinetic energy of atoms and the molecule increases. The more is the temperature, more will the temperature increases, the molecule with more kinetic energy will be increases. Temperature increases, kinetic energy of the molecule increases. If you increase the temperature of the molecule with more kinetic energy will be increases. Thereby, as the number of molecules with more kinetic energy increases, because of the rise of temperature, the rate of the reaction also increases. Now consider the graph. Here the y-axis, the fraction of molecules, and here it is the kinetic energy. Here the first graph for 298 Kelvin, the first graph for 298 Kelvin, as the temperature is lower, the molecule with more kinetic energy is less. The molecule with more kinetic energy is less. As the temperature increases, the molecule with more kinetic energy is more. Here the line flattens as the temperature increases. The molecule with more kinetic energy is more, thereby high threshold energy to cross the energy barrier to convert into product. It shows the effect of temperature on rate of chemical reactions, and here the more will be the temperature, more will be the rate of reaction. Like, share and subscribe for more videos. Thank you.